Hello, everyone. Welcome to the latest Julia Computing webinar, Trimming Linearization and Model Predictive Control Design with JuliaSim. I'm Misha Santamand. I'm the head of marketing here at Julia Computing. Today, I'm joined by Dr. Fredrik Bagge, Carlson, and Dr. Avinash Subramanian, and they will be demonstrating the typical workflow for a control engineer using JuliaSim. Before we start, a little bit of background about our presenters. Dr. Carlson is the lead of the JuliaSim control system team at JuliaHub. He holds a PhD in automatic control from Lund University. Dr. Subramanian holds a PhD from NTNU in Norway and was previously a graduate researcher at the Process Systems Engineering Laboratory at MIT. As we go through things, please, if you have questions, enter them into the Q&A window below. We'll answer them at the end of the session, or if it's appropriate to the material we're covering, one of our two presenters will jump in. So I will hand things off to my colleagues here and get things started.
Great. Thank you, Misha. I'm excited to see you all joining the webinar here today. Today we'll talk about model predictive control, an advanced control technique, and how we can employ that in JuliaSim. I'm joined here today by Avinash, and we are very excited to talk to you about the latest and greatest we have to offer in the JuliaSim control package. JuliaSim in general is our product that makes the Julia language that is already a stellar choice for technical computing. We really try to make this the language of choice for the engineer that is interested in modeling, simulation, and control. So just a brief overview of JuliaSim. We offer everything you need to build models using the ACASL modeling tool, ModelingToolkit. We also offer products to build surrogate models. If your model is very large, very complicated, and it's running a bit too slow, perhaps, we can build a surrogate of that model. That is a substantially faster version of the same model. We also allow you to build controllers, model predictive controllers, and optimize model parameters. If you have real-world data that you have collected from the system you're modeling, you might want to calibrate the parameters in your simulation model so that it agrees with reality. But today we will talk about the control library in particular. So the JuliaSim control library offers a wide spectrum of control-related features. From the simple end, we have PID controllers, all your standard linear control system analysis and design tools, towards the more advanced spectrum where we have model predictive controllers that work for nonlinear systems. They employ an optimizer in the control loop running in real time, and that's something we'll talk about today. So if we look at the block diagram here of the model predictive controller we see in the center of the slide, we have the white box at top, which represents the true system, the system we are interested in controlling. Today, that system will also be implemented as a simulation model for simulation purposes. And then in the bottom, we have the controller marked in a blue box. And the model predictive controller, I hope many of you are familiar with the basics of MPC controllers. The MPC controller makes use of a prediction model that predicts the future evolution of the system forward in time. And then it employs an optimization algorithm to optimize the control inputs so that we optimize some kind of cost we have defined how we want our system to behave in closed loop. And then out of this, we get the control signal trajectory where we deploy the first control signal action and send that to the real system. We get some sensor measurements back. Here we indicate with an arrow that we get measurements and state estimation back. And the reason we have written state estimation there as well, and not as part of the controller, is something we will elaborate more on as the webinar progresses. So if we move to the next slide, I also want to highlight that we don't only have model predictive control capabilities. We have all your standard robust control features as well, such as H-infinity, H2, LQR control, modeling of uncertainty, which is something the control engineer is very often quite keen on doing, and LMI-based more advanced synthesis methods. So we can calculate stuff like disk margin, and you can, of course, calculate frequency responses and Nyquist plots and all that standard stuff we got you covered. All right, diving a bit deeper into the model predictive control functionality in JuliaSim. We allow you to build both linear and nonlinear model predictive controllers. In the previous webinar on MPC and JuliaSim, we showed how you can automatically robustify your tuning. So MPC is known to be somewhat hard to tune. It's very often similar to tuning an LQR controller, and it's perhaps not always super intuitive. So we provide automatic robustification strategies that are available for you to use. We also allow you to model the system you're about to control in many different ways. Today, we will look at how we can build a model using ModelingToolkit. Previously, we have looked at how we can build a model using just standard Julia code, but we might also use an FMU, which is an exported piece of binary code that is produced by another modeling tool, such as one of the Modelica-based modeling tools. In the model predictive control package, we allow the user to select the solver. We support any solver that MathOpt interface in Julia supports. So this allows you to use high-performance custom MPC solvers like OSQP, but it also allows you to use more general-purpose solvers like IPOpt, for instance, if you have a nonlinear NPC problem. The user can specify and configure the discretization, so we can discretize using multiple shooting, single shooting, direct collocation, and a whole host of options are available for you there. And perhaps the most interesting feature, and which we're going to spend quite a lot of time talking about today, is how we can surrogatize the MPC controller to get a completely optimizer-free operation of our MPC. So for a linear system with a quadratic cost function, the explicit version of an MPC that does not use an optimizer is known to have a very nice and simple form where we have polytopes in the state space where we have linear control of. However, if we do not have linear dynamics or we don't have a quadratic cost function, that form of an explicit MPC is no longer applicable. Whereas our version of explicit MPC, which we just call surrogate MPC, is valid no matter what formulation of the MPC controller you have. And just a brief teaser here, we can typically, without surrogatization, solve linear MPC problems of reasonable size at around 4,000 hertz, sometimes faster, sometimes slower. It obviously depends on the particular details of your model. Nonlinear MPC problems are, of course, slightly more challenging, but we can still very often solve them at around a kilohertz. However, if we choose to surrogatize the controller, we can often reach speeds of up to 1 megahertz. So 1 megahertz is obviously vastly faster than if you have the optimizer in the loop. Today, we're going to see an example of an intermediate complexity system where we reach the order of maybe 20 kilohertz sampling frequency, something like that. But the surrogatized version is always substantially faster, and we will dive deeper into several other benefits related to removing the optimizer from the loop. All right, and with that, I would like to hand over to Avinash, who will like to dive a bit deeper into the details.
All right, thank you, Fredrik. So just to mention once again, so the MPC controller consists of 3 different pieces, 3 different models. So we have the first is the prediction model here in this blue box. The second is the actual dynamics of the plant in this white box, and then the third is the state estimator. So those are the 3 components of building an MPC controller. So I would like to present a typical workflow of developing a linear MPC problem with a nonlinear plant and observer model. So we have this 6-step procedure that I would like to present. So commonly, the first step is to build the nonlinear dynamic system model, and this is often based on domain knowledge. As Fredrik mentioned, we'll be doing this with ModelingToolkit. Following this, we would obtain a feasible equilibrium point, also a trim point, and this is done with the JuliaSim control trim tool, which commonly also formulates an optimization problem. So it uses the optimization.jl toolkit as well. Following this, we would commonly linearize about the trim point, and then this gives us the first of the three models we need for the MPC. So this gives us a linear prediction model. Linearization would be done using the ModelingToolkit linearize functionality. The fourth step commonly would involve building a nonlinear observer model for state estimation. In this case, we choose to use an uncentered Kalman filter from the low-level particle filters library. So this gives us the second piece of the MPC problem. The fifth step involves putting all the three parts together. So we formulate and solve the MPC using the JuliaSim control MPC toolkit with the linear prediction model, the nonlinear observer, and the nonlinear plant model. So the sixth step is a new feature we're excited about. So this is to surrogatize the MPC for fast optimizer free closed loop control. And this is using the MPC surrogates tool. Since this trains a machine learning model to predict the control law, we commonly use the Flux toolkit, which is Julia's machine learning library. To train, we may also want to use a GPU through CUDA, and we'll see some cases in which surrogatizing gives up to 150 times, something like 150 times speed up. Right. So the application I would like to present today is this nonlinear research civil aircraft model. So this aircraft model is an application of intermediate complexity. So it has fast nonlinear dynamics. For instance, we would need a sample time of say 0.02 seconds. Right. So just to describe it, as seen in this picture, we have it's comprised of 9 states and 5 control inputs. So the 9 states are the 3 translational velocities. So that is velocity along the x-axis, along the y-axis, and along the z-axis. The 3 rotational velocities, so that is rotation about the x-axis, the rotational velocity about the x-axis, the rotational velocity about the y-axis over here, and then the rotational velocity about the z-axis. And then the rotation angles, again about x. So in this case, it would be the roll or the bank angle. Rotation about the y-axis. In this case, it is the pitch. So it would be, for instance, pitched up during takeoff. And then the yaw angle, which is rotation about the z-axis. The aircraft has 5 control inputs that the pilot can manipulate. So this, or the controller can manipulate. So in this case, it would be the aileron, the left and right aileron. So this would be the aileron angle, the tail angle, the rudder angle, and the position of the left engine throttle and the position of the right engine throttle. So this is an example of a problem of intermediate complexity, as I mentioned. So the first step in the workflow is to perform a symbolic modeling, again using ModelingToolkit.jl. Now, ModelingToolkit.jl generally can perform acausal modeling and also has a high performance structural simplification algorithms included. It also provides an interface to the control and NPC toolkit. So generally, the procedure based on domain knowledge would be to begin by defining parameters, variables, and equations. So we would define parameters using the @parameters macro of Julia, and variables using the @variables macro and the set of equations. Following this, next step would be to build the ODE, or differential algebraic equation system, that puts everything together. So I would like to mention that this link contains a 1-hour lecture by Professor Christopher Lum, who goes through the derivation of the aerodynamic equations of the research civil aircraft model. I will now switch to Pluto notebook that shows that demos the code. Right. So just to mention, Pluto is a Julia native notebook, similar to the Jupyter notebook, but then this, being Julia native works well with the rest of the Julia toolkits. So then the first procedure would be to import in the packages of interest as shown here. And then the first step is formulating the symbolic model with ModelingToolkit.jl, commonly beginning by defining the fixed parameters to certain values. And here we have a large number of fixed parameters, which are commonly aerodynamic coefficients. So for instance, air density, the total mass, the wing area, the tail area, gravity, and so on. The get parameters macro. Following this, we would define the variables, which in this case are the states and controls. As I mentioned, we have 9 states and 5 control variables.
Avinash, I'm going to interrupt for 1 second. I got a request if you can increase the font size for what you're showing.
Is that better?
So it's a bit larger now.
Is that better?
Catherine,
so.
if you are not happy, please type again, and we can further increase the font size.
All right. So again, as I mentioned, we have the states, we have the controls. And then we could put together, we could pack these up. So the slides have a link, as I mentioned, to a 1-hour-long YouTube video that derives the aerodynamic equations. It's a 9-step procedure derived in detail that I go through over here, which I will not present in this webinar, but it's listed here. So for instance, the step 1 would be to determine the intermediate variables, determine the aerodynamic force coefficients, the dimensional aerodynamic forces, and so on. So it's quite a long procedure. And then we package everything. Into the ODE system model. So in total, this would define 118 equations and 123 states. So Pluto automatically gives us a latified version. So this
Avinash, I'm having a little bit of an audio issue with you. You disappeared briefly.
Okay, is this better? Or...
That's much better. Yes.
Okay. I'm sorry about that. Right. So this is a list of the equations that we have input into the body system. So as I mentioned, we would have in this case, it's 118 differential and algebraic equations and 123 states. So the 5 are the control inputs. So again, this is quite a complicated differential algebraic equation system to model and simulate. I mean, it's intuitive, but it's very complicated. But then ModelingToolkit provides us a functionality to simplify the structure of the system and to perform numerical simplification. Numerical simulation. So ModelingToolkit has this I/O pre-processing functionality. So it will take in the symbolically defined ODE system, a set of inputs, which in this control inputs, as I mentioned, the outputs. So here in this case, I assume all the states can be measured. And then it performs a sequence of, it employs a simplification algorithm, and it reduces this complicated system of equations to this system of 9 different purely differential equations. So There are no algebraic equations anymore. We have these 9 differential equations and 9 states. Again, this can be quite complex, but then it is just 9 equations. All right. I would like to mention that there is functionality to display the reduced system, so we can see the 9 states, the parameters, the incidence matrix, and so on. And we get this nice modeling toolkit now has the ability to present these nice descriptions on your states and parameters. All right, so moving on to numerical simulation to get some intuition for what the system would look like. So if I choose these as my initial states, I choose certain sample control inputs, and then simulate the system, I'm able to get these graphs, and then interpreting them, it's like the forward velocity of the aircraft with these initial states increases and then tends to settle down a bit. There's no sidewards velocity of the aircraft. Then the vertical velocity of the aircraft, it drops a bit, and then it settles down. So all the states settle after a while. So the second step in the workflow is to determine equilibrium points. So these are feasible trim or equilibrium points. And this is using the trim functionality of JuliaSim control as documented here. So what the user would do is put in the symbolically defined system, so the RCAM model as I showed, put in a list of inputs and outputs, put in a list of parameters, and then mention what the desired states the user would like to trim about, or trim to, would like to trim. So, and also there is the opportunity to put in a set of hard equality and hard inequality constraints. And also, since we are, so the internals of trim are that we find the closest state and controls that to the user desired states. By default, the trim functionality would return a steady state. However, we may also want to have, say, a steady acceleration or a steady banking turn and trim to that state, and that could also be provided by the trim functionality. So one can specify non-zero derivatives as well. In this case, since we want to linearize, we'll have an equilibrium point, and I would like to linearize about steady state, straight and level flight. So I would like to set the airspeed to, say, be 85 meters per second. Say I would like to have 0 side slip velocity, 0 bank angle, and I would like to be heading. So what this does, it will formulate a constrained or unconstrained optimization problem to find the closest state and controls to the user desired specifications. So returning to the Twitter notebook, the second step on trimming, we put in the desired states over here. The hard equality constraints, I would like, say, SP to be 85, certain other equality constraints, and then hard equality constraints, which in this case are the bounds. Check it also specify. There are a few other bits of functionality like specifying penalty multipliers for the optimization problem and so on. Again, fully documented. We run a trim, and then we get the different trim states about which we may rise. Right. So the third step in the workflow would be to mention linearize about this equilibrium point, and this is done using the modeling toolkit linearize tool. So then this takes in once again symbolically defined ODE system inputs, and then in this case we'll take in an operating point. This operating point is the trim point that we determined in step 2. It would return again the familiar A, B, C, D matrices, linear state space system, in this case in delta coordinates. So returning to the Pluto notebook. So here we see that ModelingToolkit linearized functionality gives us this A, B, C, and D matrices. And initially, in this case, they would be continuous named state space systems. So following this, we may want to discretize the dynamics. As I mentioned, an appropriate value for the sample time would be 0.02 seconds. So again, discretizing this linear system with a sample time is quite familiar with the familiar C to D function. We can discretize it and then get out this discrete time. Now it's a discrete time state space system, again with the A, B, C, and D matrices. So I'll pass to Fredrik, who would describe. So just to mention, we could also linearize differential algebraic systems as described in this documentation, which Fredrik will describe next.
All right, thank you, Avinash. So so far we have been concerned in this webinar with differential equations. So differential equation systems on state space form. And if we look at the equation in the top left here, we have such a differential equation where x dot, the time derivative of x, is a function f of the differential state x and a algebraic variable z and the control input u. But we may in general model DAE systems in ModelingToolkit, and DAE systems have, in addition to f, have a set of algebraic equations g. In this case, they should equal to 0, and those specify the evolution of the algebraic descriptor variables. And we would like to be able to linearize our system even in the presence of such algebraic equations. So if we just straight up and down linearize the equation system we have on the left, we get the system we have on the right, where nabla x of f denotes the Jacobian of f with respect to x. And we see here that we have 9 different Jacobians, whereas in the typical state space system we're used to, we have the matrices A, B, C, and D, and those are only 4 Jacobians. So if this makes you confused and terrified, don't worry. ModelingToolkit will, in many cases, simplify this automatically for you. In particular, in case the term on the far right in the middle, nabla u g times u prime or u dot. If that term vanishes, ModelingToolkit will automatically simplify the system for you. Even if that term doesn't vanish, there is still a chance we can do further numerical simplification after that. But there remains some situations where that is not possible either. A very common case if you are employing an inverse model for your controller. So for instance, in robotics, it's very common that we make use of a control technique called computed torque. And there we compute in advance a trajectory we want the robot to follow. And then we use the inverse model to compute what torques are required to follow that trajectory. And indeed, in that formulation, not only the positions, but also the velocities and accelerations have to be provided as inputs to the computed torque model, to the inverse model. So that's a very common example of where the additional simplification is not possible. But if you have not made use of such an inverse model, ModelingToolkit will be nice enough and simplify your DAE system into a regular state space model on linear form that you are used to and can do control design and analysis on. All right, we have also spoken a bit about uncentered Kalman filters. So perhaps not everyone is familiar with an uncentered Kalman filter. So we will build upon our intuition from the standard Kalman filter. In the standard Kalman filter, we have a Gaussian noise acting on both the dynamics and the measurements. The uncentered Kalman filter lifts this restriction slightly by allowing the dynamics function to be nonlinear and the measurement function to be nonlinear. We do, however, still require the noises to be Gaussian. And an interesting thing with our implementation of the Kalman filter is that it also works for DAE systems. So even if you have algebraic equations in the model you're trying to estimate the state for, we will still work. So for state estimation on DAE systems, there are a lot of different available options. So one is to make use of a particle filter. Particle filters are wonderful in their generality. They work in a lot of different cases, but they are at the same time computationally very expensive. Another option is to employ moving horizon estimation. And that is essentially the dual of an MPC problem. So it solves an optimization problem at each sample time, similar to the MPC controller. And that's obviously also somewhat computationally expensive. A sweet spot for accuracy and performance that we have found is to employ the UKF for DAE systems, which is comparatively quite cheap. So the next step here is just a very brief overview of how an uncentered Kalman filter works. So if we consider the covariance ellipses in the figure to the right, imagine that our current belief of the state of the system is the blue covariance ellipse. To propagate this forward in time, what the regular Kalman filter would do would just apply the linear dynamic function, and that renders the posterior distribution also Gaussian. However, if the dynamics is not linear, we don't get a Gaussian distribution in the end. In fact, we might get a distribution we can't even represent on a closed form. So what the UKF does instead is samples this covariance ellipse in a very particular point. In the literature, these are called sigma points. So this refers to the samples. You see the blue dots in the covariance ellipse. Once we have generated these sigma points for the differential variables, so for the x variables, we make use of the algebraic equation to generate sigma points also for the z variables, the algebraic variables. When we have the full descriptor x and z, we may propagate this through the dynamics function f, and that's indicated by the arrow in the illustration. And the result is a new set of sigma points that represent the posterior distribution over the state. And then we may reapproximate this as a Gaussian distribution for the UKF equations to continue. So we calculate a new covariance matrix. And all of this is packaged nicely into the package low-level particle filters, which interacts very nicely with the modern predictive control toolbox. All right, and with that, I would like to hand over again to Avinash to dive a bit deeper into the MPC formulation in our package.
Right. Thank you, Fredrik. So in this case, for the first example, I would like to begin by formulating the MPC problem. And in this case, it's linear MPC with nonlinear observer and plant. So I would package the models using this linear MPC constructor. So packaging the linear prediction model I got from the third linearization step, packaging the observer, which in this case was the which in this case is the uncentered Kalman filter, put in the constraints, the operating point, and an initial point for the observer, as well as a few other keyword arguments. So I'll show this using the Pluto notebook. So again, as I mentioned, here's the code for building the observer. In this case, the uncentered Kalman filter. We have this build control dynamics that will take in the nonlinear symbolic model inputs and give the function system and some bookkeeping, and then the nonlinear dynamics again are discretized using this Runge cutter for method that's implemented inside JuliaSim control, and this gives rise to the discrete dynamics. So again, for the uncentered Kalman filter, we would pass in the dynamics covariance matrix, the measurement covariance matrix, and control covariance matrix, and then the initial point of the simulation. Then use the uncentered Kalman filter constructor with the discretized nonlinear models, discrete dynamics. These covariance matrices, and then we would use an operating point wrapper. So what this does is help negotiate the coordinates. So between the delta, negotiate between the delta coordinates we have in the linear system and the real coordinates we have in a nonlinear observer. So this helps, this is used to negotiate that. And then you could formulate and solve the optimization problem. So in this case, I would have a set of, in this case, the constraints are constraints on the control inputs, and we would package them in with this linear NPC model constructor. So I would like to mention that the toolkit can take in arbitrary constraints. So we could have arbitrary constraints on the states and the control inputs. So once we have the MPC model, we would then formulate the LQ MPC problem with this constructor, and then pass in that gives us with this cost function. So in this way, we would put in the prediction horizon for the prediction model, the penalty matrices, so the state penalty matrices, the control input penalty matrices, a few matrices on the soft constraints. Then, so we may also want to tune the MPC control matrices for robust control, and then there's this tuning procedure that is presented in the previous webinar. With the scaled, tuned penalty matrices, and then we would put this into this LQ MPC problem. So this would take in the models as well as the other matrices. We would also, in this case, use the OSQP solver. So for the first example, where we have linear MPC without disturbance, so in this case, we have this solve functionality provided within MPC, and this overrides the common solve method. So it would take in the MPC problem, the initial state, the simulation time, so this actual dynamics. So this actual dynamics are the real plant dynamics. We may want to input in a disturbance model, and as well as other keyword arguments as documented. So in the first case, if we're to look at without disturbance, so here from the initial state at about 87 meters per second, the trim state is over here, is presented here. So we see that we are able to generate a set of control inputs that take the aircraft from this initial state to the trim state. I would also like to present an example with a disturbance. So in this case, I see that, say, from the 3rd second to the 4th second, one of the aircrafts freezes a bit, and then one of the aircraft engines freezes a lot. So it's an additive disturbance of -1 degrees and -20 degrees on these two control inputs. Again, the procedure is exactly the same as above, except now we would present this disturbance as well to the MPC controller, and then we are able to solve. So we see that we had settled in until the 3rd second when the disturbance hits, and we would need to provide the optimizer would provide us a series of control inputs that allows recovery to the trim state.
So you show there, Avinash, printouts after you have simulated the system. It says timing there.
Right.
350 milliseconds.
Right. So this is 350 milliseconds to solve this linear MPC problem without disturbance for 900 time steps, which means that the frequency is in the order of 3000 hertz in this case.
So that's without any surrogate. That's actually solving the optimization problem 900 times, right? Yeah.
Yes, this is solving the optimization problem 900 times in this 406 milliseconds. And again, this is benchmark time, so it is averaged over a number of runs. Right. So we have this example that shows disturbance rejection. I would like to mention, again, not the key part of this talk, but the toolkit already has functionality for more advanced MPC formulations. For instance, we could have a nonlinear MPC, again, with this Q MPC problem formulation. So in this case, we would take the actual nonlinear dynamics, the nonlinear observer, so everything would be nonlinear. The prediction horizon, the state penalty matrices, so on. So this would be a nonlinear MPC problem. We could also have a robust MPC problem. So this allows for robust loop shaping functionality and provides that. Then we could also have a generic MPC function, again, all documented at this link. Well, we can specify arbitrary cost functions. I'll just show what the nonlinear MPC would look like. So here, we would formulate, again, we can formulate arbitrary nonlinear constraints using this nonlinear MPC constraints constructor, formulate the Q MPC problem, pass in the discrete dynamics, and this is nonlinear, discretized nonlinear observer, so on. Then once again we can make a call to solve. Here the trajectories of states and the controls are very similar to what we got with the linear MPC. It takes a bit longer than the linear MPC. So again, because this has all the additional machinery for solving a full nonlinear problem. Right. So next I'll pass off to Fredrik, who will present the philosophy of surrogatization of the MPC controller.
All right, thank you. So MPC has been talked about in literature, indeed, for a very long time. It has been used in some industries very successfully, but there are several industries that have been very reluctant towards using MPC in practice. And I think there are several different reasons for this. And the most obvious and intuitive one is that it's expensive to solve an optimization problem at each sample instant. So it's, of course, significantly more expensive than implementing a PID controller, for instance. And that, of course, leads to limited sample rates. And if you require a very fast sample rate, perhaps MPC controllers have historically not been for you. But there are other and sometimes perhaps even more challenging problems. So we might ask ourselves, will this optimizer always converge in time? So the optimizer is an iterative algorithm that iterates until convergence. And if we look at the simple example here of a controller that is operating at 50 Hertz in a car, and we sell that car to about 1 million customers, and they each run about an hour per day for 10 years. That amounts to an absolute ton of solves. So in this case, if it's a linear MPC, it would be QP solves. And not a single of those may fail or take too long time. And that's quite a lot of things to ask of an optimization algorithm. And in some cases, in some industries, the implementation also has to be verified. So if we want to put this in a car, we might need a MISRA verification, for instance. And such verification is extremely time-consuming and expensive. And sometimes this is much more of a concern than the limited sample rate. So if we have a look at what options we have to mitigate this problem, if we start looking at the far left, we have a standard MPC controller without anything fancy, no surrogatization. This is very nice from the perspective that it offers you maximum flexibility. You can at any time tune any of the parameters in both the observer and in the MPC controller. And you can even do that after you have deployed the controller. But the broken heart here indicates that it requires online optimization. So we need to put optimizer in the loop with all the challenges that brings. If we consider the alternative in the middle instead, where I say surrogatize the optimizer, if we keep the observer, the state estimator, outside of the loop and just surrogatize the optimizer, then we get rid of the requirement for online optimization. We now no longer have an optimizer in the loop. And we can still tune the observer on site after we have deployed the controller and learned the surrogate. We can not only tune noise properties that are commonly associated with the observer, but we can also tune things like the integral action time constant if we have added a disturbance model or integral action to our system. Those can still be tuned after we have learned the surrogate. And in this case, the surrogate is a static mapping from state to control. So when we look at the optimizer, perhaps it's not immediately obvious, but the optimizer is just an implicit definition of a function that takes a state estimate and produce a control signal. So that's a completely static mapping. A slight downside here is that the objective value of the MPC controller cannot be tuned on site after deployment if we have surrogatized the controller. There are strategies to mitigate this, but it makes it slightly more inconvenient. If we go to the far extreme on the right, where we surrogatize everything, and when I say everything, I include also the observer. And we still have the major benefit of not requiring the optimizer then. And also the controller is now a single component. We don't have a split up observer and controller. But it also means that absolutely nothing can be tuned on site unless we pull some fancy tricks on when we do the surrogatization. But the broken heart here is that the surrogate is now a dynamical system. Previously, it was a static mapping. And that has a lot of quite severe implications for the training of such a surrogate. The number of inputs to such a surrogate absolutely explodes compared to the middle case here. So in the bottom of the slide here, I've written, can we eat the cake and keep most of it? And I think the middle alternative here represents such a scenario where we keep most of the benefits of an MPC controller while at the same time gaining a ton of new benefits that we will dive a bit deeper into on the next slide. So if we look at the components of an MPC controller here in the block diagram to the right, we have the system we want to control. So this would be your physical hardware, the airplane in this case, labeled P for plant or process. And out from that comes a measurement, Y, that is fed into the observer. And the observer here is drawn as its separate box. So this would be your Kalman filter, uncentered Kalman filter, so on. And that produces a state estimate, XH, that feeds into the MPC controller. So in this block diagram, the MPC controller is just the optimizer, essentially. So if we would be to replace that box, the MPC controller, with a surrogate, then we still have the controller is still a dynamical system, but all the dynamics are in the observer. And the MPC box, the surrogate box, is just a mapping from references XR and state estimates XH to the control output U. So that allows us to use a standard machine learning model, for instance, a neural network. It doesn't have to be a neural network, but it's one of many options. And crucially here is that all concerns we may have about having an optimizer in the closed loop, they are completely vanished now. So we have deterministic sample time. The neural network always takes the same amount of time to run. It's not only deterministic, it's also often significantly faster than running the optimizer. And it's also significantly easier to verify the implementation. So a neural network, for instance, is just the matrix multiplication. It's much simpler than an optimizer. So I would like to press on a point here that verifying the implementation is not the same as verifying whether the controller stabilizes the system and is robust and so on. That's a separate concern that we do not mitigate with this strategy. But verifying the implementation is still significantly easier with a surrogate. And as I said before, that the controller remains partly tunable. And I think this is critical to actually make use of this in practice. Very often we tune our controllers in simulation as a first step, and as a first step only, right? Because when we deploy the controller on a physical piece of equipment, that equipment is gonna differ slightly from the simulation model, and it's not gonna work as well as it did in simulation. So we need to have some form of tuning capabilities left when we put this controller on the factory floor, in a car, on a robot, on an autonomous excavator, in an airplane, and so on. So some challenges that remain. We haven't solved all problems here. We still need to verify and build trust in the surrogate, and that's where our tools for verifying surrogates come into place. We have some slight challenges left with updating constraints and references after we have trained this. So if we have foreseen ahead of time that we want to be able to update constraints, then we can accommodate that. But once you have trained the surrogate without that functionality, the functionality is not there. So that's a challenge. It's also slightly more challenging to include things like reference and disturbance preview, where we have future knowledge of references and disturbances, which we might sometimes have. All right, so to wrap up on the kind of the intuition behind surrogatization of MPC, I would like you to look at it as an enabling technology. So very often control hardware is resource constrained. So even if we look at a fancy piece of equipment like an industrial robot that is quite expensive, might cost $20,000, $50,000, it still very often use a many years old CPU that might have been slow already when they put it into the robot for cost reduction purposes, right? And that might not be suitable for running a high sample rate MPC controller. But a neural network, if we choose to replace the optimizer with such a model, requires only multiplication and addition, crucially no division here. So some CPUs don't even have native division operators. So a neural network can still run reasonably fast on such extremely resource-constrained hardware. And even if we have a possibility to run the MPC controller fast enough in theory, the CPU that the MPC controller is running on might have to do a lot of other things at the same time. So in a robotic context, it might have to do trajectory planning, collision detection. It might even have to do quite expensive things like computer vision. And all of that has to fit together with the MPC controller, and everything has to return within the hard deadline. And the concern about the optimizer being in the loop is in fact real. If you are a control engineer and you would like to push for an MPC controller and you approach your manager, they might look at you with some skepticism when you say that there is an iterative algorithm in the loop that has to always converge and always be fast enough. And with the surrogate, we have a completely deterministic runtime. We have a license-free product, so you don't require an optimizer with a license that may or may not be compatible with how you ship your product to your customer. And the verification of the implementation is significantly easier. And so far, I haven't spoken too much about this faster sampling rates. So that is obviously still something that holds, and still obviously a very big benefit with the surrogatizing the MPC controller. It really makes MPC controllers viable in a lot of applications they haven't previously been viable. So once again, I am from a robotics background, so many of my examples are from robotics. In robotics, we typically split up the control system into two, where we have an inner control system that controls the servo motors. Those might run very fast, 1,000 hertz, 10,000 hertz, for instance. And then we have an outer control loop that handles the trajectory generation and planning and stuff like that, and that runs slightly slower. And that is a beautiful approach, separation of concerns, and it's good engineering practice. And that has worked for a long time. But it also involves a lot of moving components. So now you have lots of different separate software components, the PID controllers, the high-level controller, and those need to interact. And even if we design them with separation of timescales, they are still not perfectly separated, and they can never be. So a sufficiently fast MPC controller, if we allow ourselves to dream, could essentially simplify the workflow in a lot of cases and allow you to replace a hierarchical controller that has a lot of complexity with a single box. All right, there are other challenges related to actually realizing that in practice, but this is certainly one key step towards making that happen. And a longer prediction horizon also typically implies better stability properties. So to make an MPC controller stable and robust, we can employ things like terminal constraints. We obviously support that in the toolbox. But for the control engineer that is tasked with implementing such an MPC controller, it might still be quite daunting to dig through the literature and find exactly what they need to to figure out and prove that their MPC controller is stable. And with a longer prediction horizon, we typically for free get better stability properties. All right, and with that, I once again leave over to Avinash, who will dig into the details of surrogate training.
All right, thank you, Fredrik. So, so just an overview of the MPC surrogates.julia package that comes within JuliaSim. So the idea is you could define a structure of your neural network. So for instance, you could mention what width and depth of the neural network you want. We have good defaults that depend on the problem, and this is something that the user could input as well, given certain activation functions, for instance, TANH or ReLU, or again, the user has this functionality with nice defaults. And then also the machine learning training parameters. So for instance, the learning rate, the optimizer, the batch size, the number of epochs. And again, if we want to train with a GPU, whether to use a GPU. Then the functionality would be to basically pass in the MPC problem, these arguments, and it's mentioned number of training trajectories, number of test trajectories, and then sample the inputs, the initial points, the box in which they need to lie, and the optimizer for training, sample method, and so on. And then there's a get surrogate functionality that returns the trained neural network surrogate. So again, returning to the notebook, we could have this surrogatization of NPC with the neural network width, depth, parameters, and so on. And then we could train the number of training samples. So again, in this notebook, we just used fairly few, and then batch size and so on. And then we call this get surrogates function, and this returns this neural network with the training data and the test data. So it would run plus under the hood. So for this particular notebook, we did the training took a few minutes. So we did it outside the notebook, and then loaded a surrogate into the notebook. So so then we could provide a comparison of the surrogate that we trained. Again, in this case, we trained it with the GPU and then loaded it, and then compare that with the NPC controller that I showed right above. And then this gives all the states. So all the states and the controls. So for instance, this is the forward velocity. The blue is the with a regular optimizer, and then the red is the surrogate. And we see, at least visually, a very, very good match. We're able to get a very, very good match between the surrogatized linear MPC in this case, and then the surrogate. And then this comes from, right, and we can get this training. And this is on a fairly intermediate complexity example with disturbance that the surrogate has never seen the disturbance before during training. So even in that case, we're able to match the optimizer results very nicely to the eye. Again, we can calculate the frequency at which we can run the surrogatized MPC. In this case, it's about 23,000 hertz, and this is a number we're working to increase even further to allow even further high frequency. So returning to the slides, just to mention, we have this. So once we have obtained this neural network, we can train it further using optimizers like the limited memory BFGS and FluxOp tools network. We can train the neural network on a GPU with CUDA, and we also provide this additional solve method that simulates the MPC with the trained surrogate. So passing the MPC problem, passing the neural network surrogate, and call solve once again. And that gives us the results we presented. Right, so I'll leave Fredrik to wrap up.
Thank you, Avinash. So wrapping up this webinar, I would like to provide just a brief recap and maybe an outlook onto the near future. Today we have presented a version of explicit MPC for a nonlinear system, the aircraft model with 9 states and 5 control inputs. So we have called it surrogatized MPC. It's a version of an explicit MPC formulation. Something we haven't covered today, but we covered in the previous webinar on MPC is adding integral action. And in general, we can add any arbitrary disturbance model to our MPC controller. If you're interested in that, please check out the previous webinar or consult the documentation. There are several examples doing this. We also have basic code generation features. That was asked in the question and answer section also. Do we support code generation? The answer is so far yes, in limited scenarios, and it's a high priority moving target for us. So we're currently working a lot on improving our code generation capabilities so we can bring the Julia code in one form or another to your target hardware, no matter what kind of hardware that is. We also support solving model predictive control and optimal control problems for DAE systems. So today we looked at a differential system. If you have a model from ModelingToolkit that includes algebraic equations, fear not, we got you covered. MPC will work for that as well, and our state estimators also work for that. Some upcoming features we're excited about providing in the future is what we call click and surrogatize functionality. Today we looked at the code interface where the user writes code that tells the system how to surrogatize the model. We are looking into providing a graphical user interface for this to make it significantly easier and also to make it easier to explore the functionality so that what you need to provide becomes obvious in the graphical user interface. We're also working on distributing our data generation for training these surrogates. So the current surrogate that we showed in the end, it took about 10 minutes to train on a single core. But with the JuliaHub, we offer elastic compute, so you can on demand spin up multiple machines and have massive parallelism to train your surrogate. So you can have a properly trained surrogate of a model predictive controller in your hand within just a few minutes. We also provide some robust MPC features in our toolkit. They are currently already there. There is some tutorials available in the documentation, but there are several other robust formulations of MPC, and they might be useful in different contexts. And we're looking forward to including several more of those in our offering. And with that, I would like to thank you, Avinash, for excellent presentation. Thank you, Misha. And thank you to the audience who have joined us here today. And yeah. Thank you.
Thank you.
Okay, I just want to open it up. I know we're a little over time, and I know you guys have been answering questions in the Q&A, but I just wanted to give us a quick second to see if there were any additional questions that we could help or answer. If anyone didn't see it, the previous webinar that Fredrik mentioned is available on the Julia Computing website in the resources section. And you can take a look at it there. And I'm not seeing any questions pop in, so I'm just gonna say if you do have anything, you are welcome to reach out to us. Thank you, Fredrik, Avinash, for presenting this, and thanks to all of you who joined. We'll be setting up a follow-up email that will include a link of the recording so you can view it. And again, you can always reach out to us if you have additional questions. I'd also encourage you to keep an eye out for our upcoming webinars. We have an upcoming model optimizer webinar from JuliaSim and some exploration of JuliaHub's workflows. So some good stuff coming up around the corner. So thanks, everybody. I appreciate it. Thank you for joining us, and thanks for presenting.